March 8th. Let's see, March 1st, 8th, 10th. Is it March 10th? So March 3rd. Okay, getting the announcement. So how are we doing? Yeah, now it's close enough to time to start. Okay, so we have some announcements. So I talked to Brendan Wart, who's at CRC, and anybody who wants an account on the CRC clusters, you just have to request one, you'll get one. And you can put our class down and me as a sponsor if you want. And you could do that outside of class too. So anybody can get one basically. And if everybody wants one, I can just email the class list too. So we offered that. Classroom. So I requested another classroom so that we wouldn't have this problem of trying to fit into a microscopic room. We've been reassigned to Dewey 162. So I was thinking maybe not next week, but the week following, we'll transition to at least Monday, we'll try a lecture, in-person lecture. It'll still be on Zoom, so you don't have to go if you don't want to, but so keep that in mind. I don't know what this room is like, Dewey 162. I have to go take a look at it, see. But in any case, the registrar found us a new room. And at some point, maybe next week or week following, we'll start having in-person lectures at least half the time. So then problem set 5. Yeah, so problem set 4 is due on Monday. And then I was looking on Wednesday, we have the study break day. And I'm looking at problem set 5. It might take a little bit longer. So I thought you guys could use a break. So there's no problem set due on March 8th. And so problem set 5 will be due the 15th. So that's good. And a couple of you have to catch up too. So either because joined late or behind or we're in Texas. So that's another reason to have a little gap in the problem set schedule. So any questions about logistics stuff? No? Okay. So today we're going to talk about integrators. So on problem set 4, you guys are going to be calling a canned integrator, and somebody else wrote the routine for you. But that's no reason not to know a little bit about how they work. So yeah, so this class, keep trying to introduce cool physical examples of problem sets, but also we can talk about numerical methods and how integrators work is, in the class of algorithms for doing computations, numerical methods. So if this class were 100% on numerical methods, it would be incredibly dull. Well, unless you happen to really love numerical methods. But my opinion is like you mix it with the physics and it gets more interesting. So let's talk about what's called integrating ordinary differential equations and how you do that. So ordinary, differential equations. So ordinary differential equations, we can call them shorthand ODEs. And this is not working very well. So let's use this, ODEs. So what are we integrating? So we've got x dot is some function of x and possibly t. So that's a dynamical system. And sometimes these are called initial value problems because we start with an initial condition. So I have x0, and I want to find x at x of t. So this is x at t equals 0. And we want to find x of t at later times, so t greater than 0. So we want to find this. And so we're going to try and come up with some way of it. Usually you advance it. So you start with the initial condition, and you say, all right, let's figure out what our new x value is a little bit time later. And then using that value a little bit time later, you'll look for the new, the next, you'll integrate it another step, and you'll get another x position a little bit time later after that. So yeah, so there, and then you want this to be consistent with that. So this is a derivative, f is a derivative, a time derivative of x. So you kind of remember that. So the easiest scheme or algorithm is called Euler's method. So Euler's method. And so yeah, so that's, you take x of t plus h. So h is the time step. So h is dt. And we expand this. So yeah, so this is t0. So I want to know what's x a little bit time later after time t0. We could have t0 be 0, 2. But let's just expand this in a Taylor series. So this is going to be x of t0, and this is our initial condition. Plus, we now take the time derivative of this, x prime of t0. And so this is evaluated at t0 times h, because that's the time step, and we're kind of assuming that this is small. And then you can take more higher order terms evaluated at the initial condition, h squared over 2, etc. So this is just a Taylor series expansion. And so let's ignore the second. This is the first order term because it depends on h. Second order term depends on h squared. Let's just do this to first order. So we'll take this and go like this, dot, dot, dot. And now, oh, right, this, what's this? Well, this is the same thing as that, because this is the time derivative of x, which is equal to f of x. So I can now replace this, f of x naught and t naught, like that. And now I have an expression. So I take x of t naught plus h is approximately equal x0 plus f of x naught t naught times h. And so I can find the position x a small time step later from the initial condition, my function, and multiplied by the time step. And so if you integrate that way, that's known as Euler's method. And that's perfectly valid. How good is it? So, so I'll draw you a plot. What does this look like on a plot? So let's draw it, and then we'll ask how good it is. We'll evaluate the error a little bit more carefully in a second. So I have x here and t here, and I've got some function here. So this is the actual solution, x of t. And so let's call this the initial condition. So that's t0, and this is going to be x0. And so we calculated x of t plus h, which is my x value at a little bit time later. We calculated that as this times h. So this is the same thing as x prime, so it's the time derivative. So at this point, I calculate the time derivative, and that gives me a slope, because this is x prime evaluated at x naught, and then I multiply. So this line y is equal to x0 plus, that's the slope, x0, t0. And then I'm going at h later. So this is going to be t0 plus h. And now I'm just going down that line. And this is going to be the new position. So what Euler's method does is it takes the local slope and then predicts the new value based on the local slope, which is given by the function that you're trying to integrate. So, so you can see that Euler's method, which gives you this point here after time step h, isn't perfect. There's like an error here. So this thing here is the error. And when we did our Taylor expansion, the size of the error is x double dot of t0 times h squared over 2. And that makes sense here when you think about it. It's related to the curvature of the true solution. And the curvature is just the second order derivative of it. So, and that's pretty clear. So if x of t, the true solution, was linear, the Euler method would have given us the exact solution. If it's not linear, it has a curve to it, and the size of the error depends on the time step squared. So this is, we call this method a first order accurate method because the error, it's accurate to one factor of h, and it's inaccurate. The error size of the error goes as h squared, so the error is second order. And when you're classifying integrators, you classify them by how they depend on the time step. So Euler's method is first order method. Okay, so now let's evaluate this a little bit more carefully. So this gives you a feeling for what it does. And we're going to make some more complicated pictures that look like this when we talk about the Runge Kutta method. Okay, so let's look at the error again. So let's write down our equation again. We have x dot is equal to f of x t, like that. That's our equation of motion. And we want x double dot or x double prime of t0 because that's what's in the error. And so that's d of f of xt evaluated at t0 with initial condition x0. So, which is the same thing as ddt of x prime of t0. Okay, so it's the same thing, again, evaluated at t0. So when we do it this way, because the function, in many of the examples we have where function doesn't depend on time, but your function could actually have a t here. And so when you take the time derivative of this, it's df dx. It's got two terms in it, dx dt, because it's a double thing, plus df dt. And these are both evaluated at x0 and t0. So yeah, so this x0, t0. So yeah, so yeah. So this thing, so we can take the derivative with respect to this part or this part. So if our function doesn't have a second thing here, then the error, so dx dt is just f of x0, t0. This thing is f prime evaluated at x0, t0. This thing is f of x0, t0. And if our function doesn't have a second thing that depends on t, we can forget about it. But if it does, it would look like this, df dt of x0 evaluated at x0, t0. So remember this. So I write the error, it looks like that, but we could also write the error that looks like this. And this prime means it's with a derivative with respect to the first argument in the function. h squared over 2, like that. So we actually, in this particular integrator, we actually can rigorously figure out what the size of the error is for each step. And so we could actually say, you know, we can calculate how you know, what the error is for each bit of it and decide if it's adding up or subtracting. So when you look at this, pretty much, I mean, if I draw a particular function to get a feeling. So one of the things with the errors, right? So often when you're adding, so what does it mean to get an error? So when I calculate, I integrate, I'm making an error each step of the way. Do those errors add up, or do they tend to cancel each other? And so here it depends on the second derivative. And so if you have like a curved orbit, all the errors add. But if you have a sine wave and the function's going up and down, then the errors may kind of on the long run cancel out. So, I mean, so when you think about it, like, what does it actually mean? And when you think, the other thing to think about is, where is the error going to be biggest? Well, if you use a single step size integrator, the error is largest when your function changes quickly. And so, if you have a rapidly varying function, you're going to make a lot of error. It's going to mostly build up large amounts of error when the function's changing quickly. So I mean, I guess the main thing I'm thinking of is the celestial mechanics setting. These are an eccentric orbit. That's a classic problem. So think of a comet, right? So here's the sun, the comet comes in and does this. And while it's out at pericenter, or at apocenter out here, it's moving really slowly. And so x of t is like really slowly varying. So if you're using this constant step size integrator, it's not going to make a big error. So you could take big steps. And then here it's moving really fast. And so if you don't take small steps, you're going to get a really inaccurate result. So the eccentric orbit is one of these classic situations where either you figure out a different way to write the equations of motion where you're kind of dilating time here and compressing time here, or you use what's called a variable step size integrator and you adjust your steps size to keep the accuracy constant. So when you call the integrator, that's the kind of thing it's doing in it. When you call ODE int or solve IVP, if you tell it you want a particular level of accuracy, that's what it's going to do. It's going to try and adjust the step size to achieve that level of accuracy during the whole integration. So ODE int will definitely, pretty much every integrator that it's using or that you can call through it is adjustable step size.
So
yeah,
for a variable step size, then we would just relate it to the second derivative, yes?
Yeah, so you can for this particular example, you know the size of the error exactly. And the same thing's true when I do the Runge Kutta example, which I'm going to do next. You can rigorously figure it out. Often you don't know, you may or may not know the size of your error. So with adjustable step size integrators, what they often do is they take a step and they say, oh, how big is the error?
Okay.
And then they adjust the step size. So, and what do you mean, how as big as the error? What's really done, you take a step and you take twice as big a step and you compare the two and you see the error comes from the bigger one, and that lets you figure out what the size of the error is.
Okay.
And then they do the computation. So also in my lecture notes, I show you how to do that. So
okay, cool.
You'll see it. So there is a rigorous way to decide, even if you don't know these functions or you don't want to evaluate them, because it takes a while to evaluate them, right? So
right.
How do you figure it out? Actually, if I give you a scheme, the way you do it is you look at the scheme and you just expand everything out in Taylor series, every term in it. And then hopefully the low order terms cancel and leave the last term that's left behind in your Taylor expansion is the size of your error. So you can just crunch away with Taylor expansions on any scheme and figure out how accurate it is. And that's how they're developed. They're developed so that they cancel out all the low order terms to
cool.
achieve the high accuracy.
Okay, right.
Yeah, there's nothing magical. It's just Taylor expansions, these
Right.
numerical algorithms. So they're nothing too fancy. So for these type of integrators. So, okay, so where was I headed on there? So I talked about error. Yeah, so let's move on to the midpoint method. How do you do better than the Euler method? Before we move on to the Euler method, so I know this is kind of jumping ahead a little bit. The Euler method is just, so nice and simple. It's like the first thing you do if you're trying to, come up with a solution. So problem set 5, I'm asking you to look at what's called the Kuramoto model of oscillators. An oscillator, so we have an oscillator. Oscillator is a harmonic oscillator. But you can describe a harmonic oscillator as a phase. So theta x is oscillating with a sign, but the phase theta is just increasing with time. So theta is omega t, or actually let me give it a different omega t. So harmonic oscillator plus a constant, I guess, right? So this is angle as a function of time. Let's do that, theta of t. So phase. So harmonic oscillator you can think about as just something that with phase or angle that increases linearly in time at an angular rotation rate omega, and then x is equal to cosine omega t, for example, with maybe an amplitude in here if you want, and then x dot is a omega sine omega t, for example. That would be the solution. Okay, so if we're thinking about harmonic oscillators and they're coupled, we have phases, and the phases can influence the phases of other harmonic oscillators. So theta I is the phase angle of the ith oscillator there. So consider a system where we have n oscillators. So what I'm going to mention right now is the Kuramoto model. So it's n coupled oscillators. Supposing the oscillators don't influence each other. So if I have theta I dot, which is how fast the phase changes, all it is some frequency. And that's a harmonic oscillator, just the phase increasing in time. The solution is theta I is equal to omega I t plus a constant. Okay, so that's a boring uncoupled oscillator. So if we want to do coupled oscillators, we need to put in some kind of coupling term. And if I just sum over all oscillators, that is the Kuramoto model. So if the oscillators are in phase, then this sign is 0 and there's no change. But if they're out of phase, then there's some term here that affects how fast the angular velocity. And this gives coupling. So J goes from 0 to n minus 1 if I have n oscillators, and the first one is the index of 0. And these, so that's a coupled oscillator model. So the sine function, you could have other functions here. The sine function is the one, and you could also have this k parameter. So k is an interaction strength. And why these are the intrinsic frequencies. That's if they aren't affecting each other. And so if k is 0, you get back n oscillators that just run along at their own frequencies. So the sine function, so because these are phases, angles, you have to make it so the thing is periodic across 2 pi. And so the sine function does that. And so you can make more complicated functions here, but people like to use cosines and sines just so you get things that don't depend on theta to mod 2 pi. So this is like one of the simplest models you could think about for coupled oscillator systems. Okay, so why am I mentioning the Kutta model? So your goal is to code this up and look at what happens. And that means if I start, the initial conditions would be a set of angles, one phase for each of these oscillators. And then you want to update it in time and see what they do. And so this equation, you need to turn this equation into a way of finding out what the new phases are. So the Euler method is equivalent to set. So now what I'm going to do is start off with initial condition. So we have initial condition. So what's my initial condition? It's going to be I, and let's give it a 0 here. I'm putting the 0 up here for each oscillator. So they're oscillator. So it's a angle for each one of the oscillators. So this tells me which oscillator. This is going to be the time step. So if I use an Eulerian method, all I need to do is choose a single time. I start off with an initial condition, and then I want to get the phases for every oscillator one time step later. So I can say theta I of n is the nth time step. So these are the phases after n steps in time. And you have to choose your dt, which is how big your time step is. So if we do that, so let's take my equation of motion here. Equation of motion. So let's look at this thing. So phi, if at the nth time step, I can approximate this as theta j n. So I have I here, I plus 1, which is like the minus theta I of n over dt, which is h. So this is the time step. So this is like x of t plus h, and this is like x of t, and this is like the time step. So you can see that this is like the time derivative, which is like dx dt. And this approximation is equivalent to Euler's method that we just derived. Okay, so let's take this, because it's the first order approximation using a Taylor series, the same thing. So let's take this, and now we'll get the n plus 1. So theta of n plus 1 of I is equal to theta n times the time step, by itself. Move that over there, times h. So let's just move this over here. So we can see that this is, and move that to the other side, is equal to that times h times this. But this is equal to this. Okay, so I have this omega I plus the sum j equals 0 to n minus 1, the interaction strength times the sine of theta j minus theta I, and these are all evaluated at the previous time step. So this is the scheme. Okay, so I start with my initial conditions, which are a bunch of phases, and then I update the whole array. Like I compute this whole thing with my time step h, and that gives me the new phases for every oscillator. And so what you do is you would write a routine that you start off with an array of thetas, and you give it intrinsic frequencies and interaction strengths and the time step, and then you make the next time step, which will be a new array of phases. And this whole thing, this is the first order Eulerian scheme for solving this system, which is known as the Kuramoto model for coupled oscillators. So this K, actually, I put a constant here, but it could be a matrix if you want. And so what's interesting about the Kuramoto model, it's a model for synchronization. So if you have like a bunch of fireflies or something and they're influencing each other, then they can all start to flicker at the same time, same period. So any type of system where things synchronize can, one model for synchronization is the Kuramoto model. And then one of the nice things about it is it has this thing called the global order parameter, and that's why it's named. It's actually Kuramoto data, maybe. A couple of people worked on it in the 80s, and they showed that you could classify the solutions in this nice way. So, so these are globally coupled. There's no order for the oscillators. They're all influencing every other one. And so since then, people have done like networked ones and hybrid ones and much more complicated interactions to look at how they influence each other. Do you always get synchronization? What initial conditions will let you go to synchronized states? So there's a lot of questions you can answer, but a lot of it's explored numerically. And so that's our problem on the fifth problem set. But you have a couple weeks to think about it. And the reason for bringing this up is that it uses the first order Euler method for solving ODEs. And the only complexity here comes is that we have n of them because we have n oscillators. So any questions? Okay, well, butt in if you have questions. So I'm going to move on now. We're going to talk about the midpoint and Runge Kutta method. So let's get out of the first order setting and we'll make a second order accurate integrator. So that's what the Runge Kutta or midpoint method will give us a second order one. And the Runge Kutta one, you can then generalize and make higher order ones. So more commonly, you'll see fourth order or eighth order Runge Kuttas used, but they're derived in the same way as the midpoint method. So I'm going to show you how to do the midpoint method. Okay, so going back to our system of x dot is equal to f of x comma t. So this is our dynamical system. So I'm going to write the function, and I'm going to expand it. I want to expand it around, not around t0, but I'm going to expand it around t plus h over 2. So we're going to move this over. Can you see this? Oh, my internet is not happy. Oh, here we go. So I want to expand around t0 plus h over 2. So that's why it's called midpoint, because it's halfway from t0 to h, which is where you want the new value of x when you're up, you're doing the next time step. So let's write that out, x of t plus h. So I'm expanding around this, but I want the value at h. So it's actually x0 of t plus h over 2. So I'm doing the Taylor series around this time. Plus, so the distance in time from this location is h over 2. So this is the first term in the Taylor series. And now we're evaluating at t0 plus h over 2. And now we have a h over 2 squared, the second order term with a half in there. So the second order Taylor series is the second derivative with the distance squared divided by 2. So this is the distance squared divided by 2. And now I want d squared x dt squared evaluated at where I'm doing the expansion, t0 plus h over 2. Yes. And higher order terms, h cubed. So this O function tells me that my next term, if I had done the Taylor expansion one more, I would have gotten a d cubed x dt term with h cubed over 2, h over 2 cubed with 1 over 3 factorial. So that would be the next term over in the Taylor expansion. Because it goes as h cubed, I just wrote it out as order h cubed. So what I'm going to do now is derive a second order accurate scheme on the size of the error is going to be h cubed size. So that's this. So now let's take the next term. So I expanded t plus h, which is what it is after the full step. I want to expand this. I want to expand x on the other side of the midpoint. So just at the beginning of the time step. So this is again like this, because I'm expanding around t plus a half, which is the midpoint. But my distance to my expansion point is in the opposite direction because it's on the left side of the interval. So this is t0. Here's t0 plus h. And this spot here is my t0 plus h over half. This one, I wanted values here, but I'm expanding around here, so the distance is that. This one, I want it the other way, so it's going to be like this. dx dt, again at t0 plus 1 h over 2. And this term is going to be the same because the distance is, it's a square, so it doesn't matter that it's minus h over 2. So h over 2 squared 1/2 d squared x dt squared, evaluated at t plus h over 2. Okay, so there's nothing weird about that. So now let's subtract these two things. So yeah, so we'll subtract them. So I have x of t0 plus h minus x of t0 is equal, these two terms go away. These two terms go away. And those two terms will add. So I get h dx dt at t0 plus h over 2, like that. And I can rewrite that as x of t0 plus h, which is my new value that I actually want, is equal to x of t0, which is x0. That's my initial condition. So this thing is h, and this is dx dt, right? But this is my equation of motion. So I can write this as f of x at t plus h over 2, comma. So let's move this. So this is at t plus h over 2. So I need, this is equal to that, but I have to put in whatever x is at the midpoint and the time t plus h over 2, like that. And now, what about our order h cubed? So this, if we use a scheme that looks like that, it doesn't have any h squared term. So it's accurate to second order, and the error is h cubed. So it's a second order accurate scheme. And then the only trick is I have to tell you how do I evaluate this thing. And once I tell you how to evaluate this thing, that will have the scheme done. So that's the only thing we need to do, is figure out how do we evaluate this. When we evaluate this thing, we only need it to be we only need it to be first order accurate, because we're multiplying by h. And so if we have second order terms in here, they'll be the same size as this. So we only need this function to be correct to first order in h. So that'll help us do that. And so I'll try and keep that there. So let's look at this thing in the middle. So x, is it t0 here? X of t0 plus h over 2. we can use the Euler scheme, and that's equal to x of t0 plus h over 2 times f of x0 t0. So that's the Euler scheme again, because we're only h over 2 away. Euler scheme and plus order h squared. And so when I said we only need to evaluate this thing accurate to first order, this is accurate to first order. And so I can, so I can now take this thing and write it as this part I can put inside here. That thing, x of t0 plus h over 2 f of x0 t0. There. Okay. So let's rewrite this scheme out. I'll write it in a somewhat different form. It looks like this. So k1 is equal to h f of x0 t0. k2 is equal to h times f of x0 plus k1 over 2. So this thing is what's in here with a 2 times, and it's also t0 plus h over 2, like that. And this whole thing is, in fact, this term. And then we get the final x of t0 plus h, which is the final value after a single time step, is equal to x0, or x of t0 plus k2. So that's the recipe. It seems kind of magical, but you could then check, is it correct to third order? And so let's write this down, order h cubed. So it's accurate to second order. You can check that this in fact is accurate by Taylor expanding each of these expressions out, sticking them in the final thing, and then seeing everything cancel out that goes as h squared, and you'll see that it gives you the correct solution. The first terms that will not cancel out will be h cubed. So this method is called the midpoint method. It's also called equivalent to what's called the second order Runge Kutta method. So let me draw a picture to explain geometrically how it works. So the way I've written it here is because you can generalize what we just did and come up with an even more complicated one that uses midpoints, 3 midpoints, divides the interval up, and that would be called the fourth order one. And you can also do an eighth order version of this. So these are ways to do more accurate integrators. So let me draw the geometrical picture. So we have t here, and we have x, and we draw our curve. This is x of t, and here, this is going to be t0, and this is going to be x0. That's my initial condition. And before, what we did is we just got the slope here. So let's take this to be t0 plus h. So we want the new x value. This is the exact solution. Before, what we did is we just took this slope and we calculated that, and that gave us the Euler method. So now what we're going to do is go to the midpoint. And we're going to use the Euler method to get the new value here. So it's as if we used the Euler method, but we only went to t0 plus h over 2. But now what I'm going to do is use f of x with x computed here. And so since x of t is f of x, or x is the, since f of x is the slope, if I take this x and put it here and compute the slope, here's the slope at this point. Let me use another marker. I'll estimate the slope at this point using that x value. So remember x dot is equal to f of x. So if I use the function, I get the slope. So that's this. And now I'll take this and instead use this slope. So let's make a parallel line. That's parallel because it's got this slope in it. And we'll use that slope to take our full time step. And so we get this point here. And so this point is the point we'll get using the midpoint method. And that's also equivalent to the second order Runge Kutta. Okay. Make that look like it's equivalent to the slope computed at the midpoint from the midpoint position. So the picture shows you this error, which is order h squared, is bigger than this error, which should be order h cubed. So the plot makes it look like that's reasonable. And it takes more computations to figure out exactly what the error is, but you could, using a Taylor series, figure out how the error depends on f, your function f. Yeah, so that's the midpoint method, Runge Kutta method. So let me write down. So are there any questions on the idea? I mean, you don't actually have to write this, but you could write it if you wanted to. So if you wanted to, you could do problem set 5 with the second order method, but you don't really need to. So do you need to? So it depends. If you're doing a long integration, you don't care if you have you're not computationally challenged in the sense that it's not taking you very long to get your results, make the step size small and just integrate a lot of steps, then you can get away with the first order method. And so with the Kuramoto model, it's not so hard to see synchronization happen. And you take 1,000 steps or something and you'll either see it or you're not. Assuming k is not infinitesimally small, but you can solve that problem with a first order method. Check whenever you're using you could say, I need a better method because it's taking too long to get the accuracy I need with a low order method. So there's a trade-off. If you use a higher order method, like the Runge Kutta, you had to calculate K1, K2, and then the final thing, whereas the order method, it was a single calculation. So you have to do more calculations to do the higher order method. But if you're integrating over a length of time and you need a certain accuracy, it'll save you. You can actually add up how many computations do I need, and the higher order method will usually win as long as your calculation is a certain length of time. So even though it takes more computations for the same level of accuracy, you'll be able to do it faster. So if you're limited, meaning you find you have to, usually what happens is you're impatient. I'm always impatient. So I write the simplest possible scheme ever, and I look and I see how well does it do. I push the step size up until it breaks. And then I know exactly when it's screwing up, and then I put it below that to do my actual work. If that takes too long, then I have to stop and say, okay, I need a better integrator. I need a better numerical method. And I have to spend the time writing it or finding one that will let me do a more accurate way to carry out the calculations so that it will run faster. So I encourage you to kind of do that when you're tackling a problem. Figure out how your numerical system breaks, run it to the limit, and then set, because your time is important, so you want to do it just below the limit where you believe your results. So I know for sure the Kuramoto model will work with the first order method, and that's, you know, one of the reasons it's in the, but, you know, keep in mind, you should check always, whenever you're running anything, the easiest thing to do is have the step size or double the step size and make sure you get the same answer. If you don't get the same answer, you know you have a problem. Okay, so any questions about the second order Runge Kutta method?
You say you can also generalize it to more order, but if you generalize it to more order, which gradient are we using to do the final estimation? Like,
the Kuramoto model, yeah. So you know the functions, so you could use the midpoint method with the Kuramoto model if you want to. You just have to write something a little bit more complicated.
Maybe I'm not stating myself. Okay, so if you are using the 4-point method, you're going to have the midpoint of the midpoint again. Are you using that slope to do the final estimation, or the combination of all of those 3 middle points?
Yeah, so to get the fourth order Runge Kutta from the second order one, so I'll write down what it looks like and how it's derived. I'm not sure if it's just straightforward saying I'm going to divide it up and then use the midpoint multiple times. Really what you need to do is do a Taylor expansion and arrange it so all the terms cancel out. So I'll write down what the fourth order Runge Kutta looks like. And so I don't remember offhand the mechanism for generating the next order from the previous order one. So we could look that up, but I did not put it in my lecture notes, so I don't remember what it is. So the fourth order Runge Kutta looks like this. X0, T0, and now we have the next one, K2 is HX. It looks similar. K1 over 2, T0 plus H over 2. So again, we're at the midpoint. Now, what do we do for K3? K3 is H of F of X0 plus K2. So we're using the point here, and it's of half T0 plus a half. But we're still at the midpoint here. Then K4 is H of F, HF of X0 plus K3. So, but each one keeps depending upon the previous position of the next one. But this one doesn't have a 2 in it. T0 plus H, and now we're no longer at the midpoint. And then the final thing depends on X of T0 plus, and now it's a sum. 1, 6. So each one of these are now weighted separately. K1 plus 6. No, 2. 2K2 plus some numbers of K3 plus some numbers of K4. And what are those numbers? It's 1 and 2. So that's the fourth order Runge Kutta. So midpoint here, but each consecutively done. So this is not obvious how it's decided here. And I think I have this right. And then this one is at the end of the interval, but again, done at the position in the middle. So how do you find this other than just saying, I'll write the positions out in different places and make sure the Taylor series cancels out. So we can look that up. We should look it up. You curious? We'll look it up. I'll look it up for you guys. I'll answer the question. How do you get the fourth order Runge Kutta out of the second order one? Yeah, I know how to check it, but I don't know how to derive it. Okay, any more questions on the, because now we're going to talk about errors, a little bit more on the errors.
Yeah, so if you use like a first versus a second versus, for example, the fourth order, how much longer would it take to use such a scheme as the order increases? Okay,
well, I guess that's exactly what I was going to talk about next. So answer the question, perfect order for the next thing I was going to talk about. Okay, so supposing the error, it depends on some constant times h. And so if n is the order of the integrator, then it's n plus 1. So the first order integrator, what I was calling first order integrator, is first order accurate, which means the error went as h squared. So n equals order of integrator. So we can invert this equation, right? And we can say error over some function, over some constant to the 1 over n is equal, n plus 1 is equal to h. Okay. So so supposing I have a time interval t, time interval t, 2 t's here. So
what is C in this case?
C, yes, so that's a, so we evaluated C exactly for the Eulerian method. Remember, it was x double prime of t0, which then turned into f prime times f. So this is some number that depends on the function.
Okay.
Okay, so I'm just approximating it as something. I could have put a proportionality sign there, but yeah, and you can, if you know your scheme, you can calculate it because you can expand everything out with the Taylor series and figured it out. Or if you don't want to, you can just take the integrator and integrate one step, then integrate half of that twice and look at the difference. And the difference will let you solve for C. Actually, so if you want to figure out what C is, you can numerically while you're doing the integration. And that's what these variable step size integrators do, actually. But so we're going to say this exists. And it's not going to be the same as you integrate around the, keep integrating, it's going to vary. But let's just ignore that detail and just say there's some typical C that's in the problem. And we have an time interval t. So the number of steps that I need to do with step size h. So supposing I need to integrate a typical time t, then the number of steps is just t divided by h, right? So that's the number of steps. So right. So going back, so now we have to decide. Let's see. So yeah. Okay. So we set the error to be the minimum possible. So suppose you know what error you want to put up with. Then you use this equation to figure out what your time step is. So if I have a second order integrator, then I need 10 to the minus 7 accuracy or something, then I can figure out what the time step is. And then I can figure out how many time steps I need to do the calculation. So you can see that this formula, the needed time depends on the error divided by this constant, which presumably would be similar for the two integrators, maybe not, but divided by this. And so if your integrator is higher, then this thing, it makes h, you can effectively take bigger steps, right? Yeah, you can take bigger steps for higher order integrator. So let's do an example. So for a second order integrator, then so second order, then this n is going to be proportional to error over C to the 1/3, right? With a minus sign. That's the number of steps. And if I have a fourth order, then n, and it's not really proportional. Well, it's going to be t times that. So it's like n is equal to t times the error over C to the minus 1/5, right? this is going to be fewer steps, right, than this one. Then you can say, how much time does it take me to do the calculation? And supposing it takes, so when I wrote down the Runge Kutta recipe, you could get a feeling for how many floating point calculations was it to do the fourth order compared to the second order. And you don't need a very large number before you win in terms of computation time to go up in the higher order. Higher order integrators definitely saves you time because the number of computations is beat down by this larger or this much smaller number here than this one. So yeah, so supposing your error is 10 to the minus 15 or something, which is like floating point calculation, and say C is of order 1, then 10 to the minus 15 to the 1/3 power is 10 to the minus 5. So that's 5. So this would be 10 to the 5 if everything else was of order 1. But if 10 to the minus 15 to the 1/5 is 10 to the 3. To the minus, so that's 10 to the 3. So we would have 10 to the 5 versus 10 to the 3 in these two. And you can see that that's 100 different, which is big. So you would need, in order for you to choose this one, you would need to have 100 fewer calculations per step. If, and of course this would get even worse if T was long, for example. So does that kind of answer your question? How long do you need?
Yeah, no, that's what I was wondering. Thank you.
Yeah. So that's what happens. So yeah, so when you call these integrators, that's what's going on underneath, except for the variable step size bit. So let's talk about this variable step size bit. How much time do we have? Oh, we have time for that. So far I've only talked about single step size integrators. So yeah, variable step size integrators are great, unless you care about conservation of energy. So that's the next. So interestingly, so now I'm going to talk about how you choose your step size to achieve the same level of accuracy. First, you figure out what that coefficient C is, and then once you know what the coefficient C is, you can invert your error equation and find out what step size you need to achieve some accuracy. So you do this double step size thing to find the coefficient C, and then you invert the equation, you get the time step you need to get your accuracy. Yeah, so interestingly, in celestial mechanics, we often don't use variable step size integrators. So that's a subtlety. So, and the reason for that is we're integrating for a really long time. And so far, we've just talked about integrators to be accurate to certain orders. We haven't talked about whether they're really any good at conserving energy or not. And in fact, they don't. So if you take any of these integrators, even if they're really quite accurate, they're not going to conserve energy. So what happens is, you integrate particles and you want it to stay in an elliptical orbit, but it doesn't. It starts spiraling in or spiraling out. Actually, often they spiral out. It's as if they gain energy. So people often, what they do is they make this trade-off and they say, I want to use an integrator that conserves energy because things like resonant behavior and chaotic evolution are more important than having long-term, having it be accurate to some order over a certain length of time. And so what's used in celestial mechanics are what's known as symplectic integrators, and they just conserve quantities. And those, so with a regular integrator, high order variable step size integrator, they tend to veer in one direction, so you lose energy, the error tends to keep increasing in the same direction. Whereas if there's a conserved quantity, the errors tend to be either positive or negative, and they cancel out in long periods of time. And so these, even though the symplectic integrators tend to be fixed step size integrators, they're very well behaved. They integrate some function that's similar to the real one. It's not the real one. they integrate something that obeys the conservation quantities or similar quantities. They conserve something that's like an energy. It's not exactly the same energy. And the errors cancel out over a long period of time. So that's kind of odd when you think about it, despite the fact that, you know, if you want an accurate thing, you tend to go to variable step size. But if you want something that's accurate over long periods of time, you may not use a variable step size integrator. You may stick to constant step size integrators. So the other setting, you know, when you look at the Kuramoto model, you have n oscillators advancing and you need them to interact. So you need to integrate them all to be at the same time in order to let them interact. So grid-based things, you can think of the Kuramoto system where you have n oscillators interacting. They're not actually on a grid, but you need them to be all at the same time so that you can compute the interactions on them. And the easiest way to do that is to advance them at a constant step size, a fixed step size. So that's another reason. So with grid-based things or things that are interacting, you can't really have this freedom to say, I'll start taking teeny steps just to make it more accurate while it goes through some transition thing. You can't, I mean, you could decide to do that on a grid, but then you have all your oscillators sitting around waiting for that one oscillator to get around to getting through whatever's causing it to vary. It slows the whole system down. So, you know, again, the Kuramoto system, there isn't really any steep transitions where there's large changes taking place all at once. It's not like the eccentric orbit. The eccentric orbit, you're sitting out, like Pluto's sitting out infinitely far away forever, and then every once in a while it takes a swing into the inner solar system. And you don't need to take small step sizes while it's out in the outer parts of the solar system. You only need to keep track of it when it's coming into the inner solar system, where it could, say, get affected by Jupiter or something. Okay, so let's talk about variable step size integrators. So we're going to take a single step, and we'll call it 2h. And we're going to take two steps of size h. Okay, so the error for this error is going to go as c times 2h to the n plus 1, right? And this one, the error for a single step is going to be our c times h to the n plus 1. And then because I have two steps, I'll assume the error is add. I'll just put a 2 here, like that. So we compare these two, right? And yeah, okay, so I can integrate this and I can integrate that. And now if I, so let's call this the error of 2h, and the error, this is going to be 2 times h. So this is a single step, and that's 2 steps. And I can take the ratio of these two guys and solve for z, or c, right? So, and actually I don't really need to take the ratio. I can just look at the difference. So I don't really want the ratio. What I want is the difference. So if n is big, then this one is much bigger than that one, right? Because this is 2h to the n plus 1, and this one is 8. So actually, when I compare the two, the error of this is irrelevant compared to the error of that. So if I while I'm integrating, I look at the difference between doing this and doing that, I get the error. It should be equal to this, approximately. So c is going to approximately be the error in this one, which is this one, divided by 2h to the n plus 1. So that gives me this estimate for this coefficient c, just from doing these 3 calculations. Oh yeah, good. Wait, is that right? Oh, that gives me c. Yeah, that's fine. Yeah, that's consistent with my notes. And in fact, so x1 minus x2 is equal to this, and then I solve for it, I get that. So I can actually write this as x2 minus x1, which is x2 would be this one, x1 is that one, divided by 2h to the n plus 1. Okay, so supposing now we have a desired accuracy, then we have error is equal to C. So we solve for C using this procedure, and now we have an error which is equal to this. And if I give you the error, then now I can solve for the required time that I need to do my time step to achieve that precision. So when you call the integrator and you tell it there are these two parameters in ODE, and there's ATOL and RTOL. One of them is relative tolerance, and one of them is an absolute tolerance. So one of them is size, like if I have X, it's delta X over X. The other one is the absolute, is just how big X is going to vary. You give it your desired tolerance level, and that's the error. And then it does this computation where it takes one step or it takes two steps and uses the difference between the two to solve for this coefficient. And then it uses that coefficient to figure out what step size it needs to do that accuracy of integration. So that's what those tolerances mean. If you integrate a long integration, your actual error is going to be larger than that. And that's because this error is the error for a single step. And if you do lots of steps, if they all add up in the same direction, which they often do, unless you're integrating something like a sine or something, then your actual error will be n steps times that tolerance level that you asked for. So you should notice that when you adjust the tolerance level. So when you do the integration for the next problem set, which is problem set 4, I ask you to choose a tolerance and see what you get. And when you say how accurate did I do, compare the difference between what you integrated at the end of your integration to the predicted value. So that problem, you actually have a function, you have an analytically solvable system to integrate. And so you should be able to see the difference at the end of the integration. So you'll get a feeling for how far off is it. And however, given your tolerance value. And it won't be so if you pick a tolerance value of 10 to the minus 7, maybe you'll get 10 to the minus 4 difference, for example. So it won't be as good as your ATOL or RTOL choice of number that you tell it. Or you could send the tolerance level more, to smaller value, and then you should get a smaller difference between the predicted and the actual value at the end of your integration. So yeah. So does that make sense? That's how variable step size integrations work. How much time do we have? We have like 1 second left. So interrupt me if you have a question. Any questions? Okay, I'm just going to make so the next topic in integration. So far, X has been a single variable. So X, we have X dot is equal to F of X T. So we just kind of assumed X was like a one-dimensional thing, but X can be a vector. So let's take like this. And yeah, I don't know. So it could be something like this, X and Y, and you would have trajectories on a plane. I could take, so I'm going to use Y and Y dot. So supposing I have Newton's equations, my double dot is equal to some force. Y. So now Y is a single. So Y is a single variable. It's like a real number, but this is a mass times acceleration. So this is a force. Then so this has got two time derivatives, right? So this is d squared y dt squared. That's an acceleration. But I can, if I do this, then I can write this is equivalent to, so let's move the m to the other side, like this. Then I can, so now this is a force per unit mass. So now I can say y, so let's write this instead as y and v, actually. So I have two variables. So dy dt is equal to v, and dv dt is equal to f of y over m. So this dv dt is equal to d squared y dt. So dv dt is the acceleration, right? So these two equations are equivalent to that, where my acceleration is force divided by mass. But these two equations I can rewrite like this: d dt of a vector y and v is equal to another vector, which is v f of y over m. And so this is in the same form as that, except with this x a vector now. So so Newtonian mechanics, or even in 3 dimensions. So for 3 dimensions, I'd have 3 x, y, and z here, and vx, vy, and vz here, and the velocities would be what you expect. So let's do things in 3 dimensions now. So we have x triple dot is equal, double dot is equal to a force, which is a vector, which is a function of position divided by m. Then let's rewrite it in this form. It would be d dt of x, y, z, vx, vy, vz is equal to, so dx dt would be vx, dy dt is vy, dv dz dt would be vz. Then v dvx dt would be the force component in the x direction divided by mass, and likewise would be the component in the y direction. That's v c divided by mass. So now my vector for this thing is a 6-dimensional thing, x, y, z, vx, vy, vz. When you look at ODE int, it's designed to be such that you can pass a vector, and then you have, when you have to design a function, you have to tell it, how do I evaluate this function? If x is a vector, then this is a vector, and so the function you write would return a it would return a vector that is the time derivative, and so you would return that. So yeah, so everything in this form, we can write all our standard Newtonian physics things in that form, as long as we think of x as possibly being a vector. So we could say integrate the pendulum, which is the example that's given on the ODE and on the SciPy website page. Actually, they show you how to do this with in this form, actually, with y and v and like that. Okay, so the next thing I'm going to talk about is energy conservation, because I'm going to give you this feeling that, we talked about high order integrators, but we didn't talk about how you design integrators that are more well behaved over long periods of time. And so the symplectic integrators are in that class. So I'll give you an example of a low order symplectic integrator, actually, that is as accurate as the Runge, second order is accurate as the midpoint method, but also conserves volume, which in some cases is equivalent to energy. And so that one, which has also got the name of the Stormer-Verlet integrator, is a workhorse for n-body systems that you care about long-term behavior, for example. But you can also take those up to higher order too. But you can't vary the step size. they require. But there's also time reversible integrators, and those have similar properties as symplectic ones. So you can see their viewpoint. You can get different, you can optimize different things depending upon what you think is important if you're doing long-term integrations. So any more questions? Because I think we're over time wise. Otherwise, you guys should be working on problem set 4, where you have a qubit to play with. And otherwise, I'll see you guys on Monday.
All right. Thanks,
Same-
Professor.
Yeah, same Zoom.
Thank you.
Yeah. Okay. Send me questions.